Welcome to Gooseberry Science and Education Videos. My name is Noah, and hanging out with me today is this little orange gooseberry character right here, our official assistant for this explainer. Together, we're going to dive deep into the fascinating world beneath our feet. Let's open up the Geologist Toolkit and really demystify rocks and minerals.
Here's the roadmap for today. First, what are minerals? Second, the Geologist's Identification Toolkit. Third, the magic of crystals. And fourth, crystal systems and habits. Let's jump in.
Section 1. What are minerals? The building blocks of our planet.
Okay, before we start identifying things out in the field, we got to know what actually separates a true mineral from, just some random rock you'd kick down the street. The textbook definition? It's a naturally occurring solid with a specific chemical composition and a distinctive internal crystal structure. So basically, it has to have a set chemical formula and a repeating geometric pattern. Oh, and while most of these earthly treasures form completely inorganically from geological processes, it's actually super cool to note that a select few are formed organically by living things, like the minerals right inside animal bones.
And this really hits the nail on the head as to why that distinctive internal structure, part of the definition, is absolutely crucial. Take a look at pyrite. You probably know it as fool's gold, and compare it to the marcasite specimen. They look pretty different, right? Well, here is the wild part. They share the exact same chemical composition. They're both iron sulfide, Fe(S)2, but because their atoms arrange themselves into completely different internal crystal structures, they become entirely different minerals. Pyrite forms in this rigid cubic system, whereas marcasite builds itself completely differently. Mind-blowing, right?
Section 2. The Geologist's Identification Toolkit. Clues to identification.
All right, I hope our gooseberry assistant is ready to play detective because we're looking at the practical, physical tests used out in the field to identify these things. Now, color seems like the ultimate giveaway when you pick up a specimen, doesn't it? And yeah, sometimes it works perfectly, like azurite. It's this beautifully dependable, brilliant blue that you could spot a mile away. But color can also be a massive trickster. Take fluoride, for instance. It can literally appear in almost any color. Why? Because of trace elements. Just a tiny smidge of foreign atoms, like we're talking 3 atoms per million, can completely change a mineral's color. So, rookie mistake, relying solely on surface color.
Which brings us to a way more reliable test, the streak test. While the exterior color is all over the place, a mineral's streak is incredibly consistent. You just draw the specimen across a rough surface, like a piece of unglazed porcelain, and check out the color of the powder it leaves behind. Take hematite. It might look black or metallic silver on the outside, but it will always leave a vibrant red streak. It's an absolute game changer for telling apart minerals that look identical on the surface.
Okay, next up in our toolkit is lustre. This is simply how a mineral surface reflects light. Broadly speaking, it's divided into metallic and non-metallic. You've got the brilliant, untarnished shine of native gold for your metallic. And then the non-metallic lustres are just all over the map. You have the vitreous look of clear crystals that resemble broken glass, or you might find a dull, non-reflective appearance that geologists just call earthy.
Moving right along, we have hardness. This is all about testing a mineral's relative resistance to being scratched. The golden rule here is super simple, but absolute. A harder mineral will always scratch a softer one, but a softer mineral will never, ever scratch a harder one. It's just a quick, fantastic physical test that instantly narrows down what you're holding.
To keep things standardized, we use the Mohs scale of hardness, which goes from 1 to 10. It measures relative scratch resistance based on 10 specific benchmark minerals. And here's a quick field cheat sheet for you. Hydraceous minerals, meaning they actually have water molecules trapped in their structure, tend to be pretty soft. On the flip side, anhydrous oxides and silicates, which completely lack those water molecules, are typically very hard and tough to scratch.
Another amazing clue is how a mineral naturally breaks. When a mineral breaks cleanly along flat, planar surfaces where its internal atomic bonds are the weakest, we call that cleavage. Just look at the perfectly flat top of a cleaved topaz crystal. Now contrast that with fracture. That's when you get a rough, shell-like break known as a conchoidal fracture. You see this a lot in glass-like materials, like quartz. No perfect planes, just totally irregular, curved breaks.
Section 3. The magic of crystals. Zooming in to the microscopic level.
All right, I want you and our gooseberry friend to conceptually shrink down with me for a second. Let's look invisibly inside the mineral at the microscopic level. See, a crystal is built from these individual, identical, repeating 3D units of atoms called unit cells.
Whether a crystal is microscopic or a massive 10-foot giant, it's literally just these unit cells repeating over and over and over again. And the specific geometric shape of that single unit cell, that is what completely dictates the ultimate shape, the symmetry, and the visible faces of the crystal we hold in our hands.
Section 4. Crystal Systems and Habits. The Geometry of Nature.
So that perfect repeating internal structure leads us directly to the magnificent macroscopic crystal shapes we can actually collect. Geologists classify all crystals into 6 broad systems: cubic, tetragonal, hexagonal, orthorhombic, monoclinic, and triclinic. These are basically defined by imaginary lines intersecting right through the center of the crystal, called crystallographic axes. By measuring the lengths of these axes and the angles where they meet, we can categorize literally every single crystal on Earth. How cool is that?
To really visualize those axes, let's look at a few examples. The cubic system has 3 equal axes at perfect 90-degree right angles. It creates highly symmetrical, perfect cubes. But nature isn't always perfectly square. Take the monoclinic system, which actually hosts more minerals than any other crystal system out there. Monoclinic translates to one incline, meaning it has one tilted axis where the lines just don't meet at perfect right angles. It's a gorgeous display of natural geometry.
Now, zooming out a bit from the underlying geometric system, we have something called crystal habit. This is the geologist's descriptive term for the overall physical appearance and growth pattern of a specimen. Basically, the external shape of a crystal or a grouping of intergrown crystals. So while the microscopic unit cells and the crystal system lay down the underlying rules, the habit is what the mineral actually ends up looking like, heavily influenced by the environment it grew in.
Let me show you just how wild these habits can get. Take hematite, for example. Sometimes it forms these incredible globular aggregates that look almost exactly like a dark bunch of bubbling grapes. Geologists call this a botryoidal habit. It's honestly kind of hard to believe that's a naturally occurring rock, isn't it?
And then you have something like this, a habit known as dendritic. It is truly a marvel. Elements like native copper can naturally grow into these complex, flat, branching, fern-like structures. I mean, it looks exactly like a pressed plant or a tiny tree branch, but nope. It is a 100% solid mineral crystal aggregate.
The sheer variety of habits is honestly endless. You can find slender, parallel strands of a fibrous habit in minerals like tremolite. Or you might stumble upon a stunning radiating or acicular habit, like mesolite, where individual needle-like crystals literally burst outwards from a common center, like a fuzzy snowball. Nature's artistry is absolutely on full display once you know what to look for.
So, as we wrap up this explainer today, I want to leave you with a quick thought. How are you going to look at the rocks beneath your feet now that you have the Geologist Toolkit? You know now that surface color can completely trick you, but a streak test tells the truth. You know that checking luster and scratching for hardness can instantly narrow down your search. And you know that inside every single specimen is a microscopic, perfect atomic geometry dictating its shape. Hopefully, an ordinary rock isn't just a rock to you anymore. It's a massive geological puzzle just waiting to be solved.
Thanks for exploring this amazing world with me and our gooseberry assistant. Keep looking down, and please like and subscribe if you enjoy the content. We are already working on a new topic.